Hi guys, in this video we're going to look at a third type of organic reaction, and that is elimination reactions. And here we've got a situation where we've got single bonds converted into double bonds, and we kick out a small molecule here. Now, type of compounds that can undergo elimination reactions would be compounds like alkyl halides, where you kick out, for example, a H and a Cl, or a H and a Br, or alcohols, where you kick out a H and an OH, and this is then forming water. So let's just have a quick look at the mechanism behind how these would occur. So if we've got, for example, an alkyl halide, we're going to make this then H, and we'll call this a Br. What would happen then is a hydroxide ion is going to come along with a lone pair and a negative, and this time the hydroxide ion is not going to attack this delta positive, and it's all dependent on the temperature and the solvent that this hydroxide ion is in. It can be made to either act as a nucleophile, or it can, as it is in this instance, act as a base, and it can form a new oxygen-hydrogen bond. Okay, so remember here that this is acting here as a base. It's a proton acceptor. In the process of this lone pair here forming a new OH bond, this here is going to form water, but then what we're going to do with the pair of electrons here, the pair of electrons there is going to form a new carbon-carbon double bond. So the two electrons that were here are now going to be here and form a double bond. That means that this carbon would have too many bonds, 1, 2, 3, 4, 5. So that means that this CBr bond is going to break. And again, this bromine is a good leaving group. We've got to have a good leaving group there. And in the process there, that's going to give us our alkene, and also give us other products as well. It would give us an alkene. It would also give us H2O, and in this case a bromide ion. So that would be, for example, an elimination reaction of haloalkane. Alcohols could also undergo similar types of reactions, but it'll be slightly different, and we'll explain why. So now let's consider I've got an alcohol. So this time we've got H and an OH. And now we can't do this mechanism, and hopefully you can see why. We can't just use a base to pull this off and kick this out, because the OH is not a good leaving group. Now, we mentioned that a little bit earlier on in the reactions of carboxylic acids when we looked at nucleophilic acyl substitution reactions. This is not a good enough leaving group. So what's going to happen now is we've got to convert this into a good leaving group. And we can do that by adding now an acid. So what's going to happen is this is going to react with a H plus. In effect, what's going to happen is you're going to get H plus. And that then is going to convert this OH into a good leaving group. So that's going to give us the following. So now we can see that we've now got an OH2, but we've now got a plus charge, because the oxygen has used its lone pair that it owned, and now that lone pair that it owned is now being used to it's now shared in forming that OH bond. What happens now is some basic group comes along and it pulls this hydrogen off. in the same way that we looked at in the other mechanism. But now we've actually got a good leaving group. We've now got a water as a leaving group, which is a far better leaving group than a hydroxide ion. So that there will give us, in this case, simply an alkene and water. So it's a bit, in effect, it's also called a dehydration reaction. This is a dehydration reaction. So that's why the mechanism is slightly different. It's because the bromine is happy to leave as a bromide ion. That is a good leaving group. So what we've got here is a good leaving group. But this OH is not a good leaving group, so we need to convert it into a good leaving group by protonating it. And now this water is a good leaving group. We can explain that because, remember how we do it, we've got to think of this is, we say this here, this species here is weakly basic. So in effect, this here has got a relatively low pKa. Certainly a much lower pKa than water would have. Okay, because if we were kicking out water, if we were kicking out hydroxide ion, we'd be looking at the following. So this species here has got a much lower pKa than this, which makes the conjugate base here a much better leaving group. So that's why you get slightly different mechanisms in the two elimination reactions.